So now we are starting with the next chapter, which is disposal of sewage effluents. Okay, so we have seen that what is the sewage treatment process in previous chapter that we were discussing. Now the sewage is treated. Now I have to uh, know that how can I dispose the sewage. There should be a proper disposal process of the sewage. We cannot just dump it anywhere. It will be hazardous to people who are living nearby. So a proper disposal process should be there. So let's start the first question, which is a river has a flow of 1000 million liters per day, 1000 mld, BOD of 5 mg per liter, and dissolved oxygen DO of level 8 mg per liter before receiving the wastewater discharge as the location. So normal river condition is given that it is flowing at the rate of 1000 million per liter per day. It has a BOD of 5 milligram per liter. It is having dissolved oxygen amount that is 8 milligram per liter. That is very good before receiving any wastewater discharge at the location. Now for the existing environmental conditions, the saturation DO level is 10 milligram per liter. That means the maximum DO at any temperature this river can attain is 10 milligram per liter. Now, the wastewater discharge of 100 mld with BOD 5 of 200 mg per liter and DO level of 2 mg per liter falls at the location. So, in the river, they have just disposed 100 mld water ml discharge and which is having BOD of 200 mg per liter and dissolved oxygen of 2 mg per liter. Assuming complete mixing of wastewater and river water, the immediate DO deficit, we need to know what will be the immediate DO deficit. So let's start. See what they have given us. Let's write that first. So they have given the discharge, which is 1000 mld. They have given the dissolved oxygen of this river, that is 8 milligram per liter, and they have given the BOD 5 as well, that is 5 milligram per liter, and saturation DO is also given, that is 10 milligram per liter. Now we have to calculate the immediate DO of the mix. So the DO of the mix, there is a relation that total discharge or I can say discharge of the mix Q of mix. Q mix will be of what? It will be of river plus discharge of wastewater. So I can say that the formula, the dissolved oxygen of the mix into discharge of the mix gives the discharge of river into DO of river plus discharge of water into DO of water. From this I can say the DO of mix is equal to QR into DO of river plus discharge of water into DO of water divided by discharge of mix. Mix is nothing but I can write discharge of river plus discharge of water. Now if I put the values, discharge of the river is 8 mld, 1000 mld, and DO of the river is 8, plus discharge of the BOD is 100 and DO is 2. Total discharge will be equal to 1000 plus 100, that comes out to be 7.455 milligram per liter DO of mix. Alright, this is the dissolved oxygen of the mix. They want dissolved oxygen deficit. That means how much oxygen deficit is there. So that oxygen deficit is given by oxygen deficit is equal to saturation DO minus DO of the actual DO, that is this much actual DO. So oxygen deficit comes out to be, or DO deficit I can say, comes out to be, actual is, saturation is 10 minus 7.455 and it comes out to be 2.545 milligram per liter. So the DO deficit comes out to be 2.55 milligram per liter. So this is the answer. Let's move on with the next question, which is the wastewater from a city containing a high concentration of biodegradable organics is being steadily discharged into a flowing river at a location S. If the rate of aeration of the river water is lower than rate of degradation of organics, then the dissolved oxygen of the river water will be. So let's do it. Let's make a curve. Okay. Okay. See this. There are 4 zones. This is your location, or I can say time. On this axis we have location or time, and on y-axis we have dissolved oxygen. Now see, there are four zones. Very first zone is first zone. This is your second zone, zone 2, and we can write this much is zone 3, and next is zone 4. Okay, see, from in these 4 zones, the very first zone is clear water. After 4th zone there will be zone 5, I can say. In 1st and 5th zone there will be clear water. Clear water, that means which is having dissolved oxygen in proper amount, so that the fishes and aquatic life can be present there. So 1st zone and 5th zone are fully clear water. And then there is zone 2, which is zone of degradation. Zone 2, first zone is clear water, next is zone of degradation. Zone of degradation. In this, the dissolved oxygen level falls due to the decomposition of organic matter, because see, this is the value of S, where we have mixed the discharge or BOD water into the sewage water into the river. So after mixing that, the dissolved oxygen of river gets consumed into the process of decomposition of organic matter, and the DO started decreasing. Okay, so the level of DO falls due to decomposition. and in this zone there will be dark and turbid water. Fishes may present, but it cannot be. It may be, cannot be there. Now, algae also is present. Okay. Next zone is, we have zone of active decomposition. Zone of active decomposition. This zone is heavily polluted. Water is very dark in this zone and turbid. DO oxygen level falls to 0, I can say, and there will be critical oxygen deficit at this place. And here neither fish nor algae will be present. So this is your zone of active decomposition. Next is zone of recovery. Zone of recovery. Here DO level, or we can say your dissolved oxygen level, increases and it may reach to saturation value in this zone. Now decomposition of organic matter takes place up to the nitrate level. Now both fishes and algae reappear in this zone. So these are the 4 zones we can say. Now in the zone like 2 and 3, almost in zone 2, the decomposition, because DO level is decreasing, decomposition rate of decomposition is greater than rate of recovery, right? That's only DO is falling down. And in zone we can say almost zone 4 or end of zone 3, rate of recovery is greater than decomposition. Okay, so what we can say is dissolved oxygen, the location is S, where they have mixing the discharge. If the rate of aeration of the river water is lower than the rate of degradation, aeration is lower than degradation, then the dissolved oxygen of the river will be, so the rate of oxygen, reoxygen, will be equal to the rate of deoxygenation. Before deoxygenation we can say like rate of reoxygenation A. If I present rate of reoxygenation as A, so before rate of reoxygenation is less. If I say in these zones rate of reoxygenation is less and rate of deoxygenation is more, so DO continuously decreases. When rate of deoxygenation is greater than rate of reoxygenation, that means rate of deoxygenation, that means decomposition, is greater than rate of reoxygenation, that means recovery, it reaches a minimum. It will reach a minimum value when two rates will be equal. This decomposition will be equal to recovery. That will be the minimum value. And after that, again the reoxygenation will be greater than decomposition or deoxygenation. So the option which will be correct is option D, is lowest at the point downstream of the location S. Option D. From this theory only there will be the next question which will also be solved. So the question is, the sag in the dissolved oxygen curve results because it is a function of rate of decrease, addition of oxygen to the stream, function of rate of depletion of oxygen to the stream, function of both addition and depletion of oxygen in the stream, and rate of addition is linear but the rate of depletion is non-linear. See, we have seen this curve. This is reoxygenation or this is deoxygenation. See, obviously your DO is a mixture of what? Both. that is your dissolved oxygen is a combination, that means mixture of addition, and we can say it is a function of deoxygenation as well reoxygenation. Then only this say it gets decomposed also, and the oxygen rate of dissolved oxygen decreases and then it increases. So we can say the both function of both addition and depletion of oxygen.